Hi everyone, I am Rajarshi Basu. My handle on CodeChef is Rajarshi_Basu. I've been doing competitive programming for a while now. I've taken part in several competitions as well, like this year's Olympiad in Informatics, Snackdown, etc. So today I'll be discussing the first 5 problems of May Challenge 2020. Um, so let's get started. The first problem. Okay, so the first 2 problems are quite simple. The rest 3 are quite difficult, like unlike last long challenge, I think. Anyway, so in this problem, I hope everyone has read all the problems, right? So in this problem, it's basically given that there are n points, rather n people on a street. Every person is identified by a value xi, and there's this COVID virus which can spread from one person to another if whenever the distance between the two persons is at most 2. So it is asked that if we wait long enough, like let everyone who can be infected, let them be infected, and let's call this size of this set be the final number of infected people. So our task is to find the smallest and largest value of the final number, provided we say that, okay, person I, if person I is infected, then what is the total number of people that will eventually be infected, right? And so among all those i's, we get the value, right? So we take the smallest and the largest value. So how do we do this? Well, let's see. Let's get a diagram. So let's say this is a person, this is a person, and then I'll give a bit of a space. So these are, let's say, within distance 2 of each other, and this person is farther away, and let's say he has, these are also, so the distance between these two are within 2, distance between these two are within 2, distance between these two are within 2, and so on, right? So we can kind of observe that there are these islands of people, right? And then there are these breaks. Okay, so these breaks are whenever there is a distance of more than 2 between 2 people, right? So this is one island, this is one island, this is one island, right? So claim is, if anyone inside one island is infected, then everyone inside the island will eventually become infected, right? Because I mean, within an island there are no breakpoints, correct? So if one person is infected, then the infection will spread all the way outwards, and like towards left, all the way towards right, till we hit the next breakpoint. So this is the next breakpoint, this is the next breakpoint, everything in between will eventually get infected. So it doesn't really matter where we start, everything will eventually get infected. So all we do is figure out what is the sizes of these islands, and then just report the minimum size of the island, the maximum size, right? So here, for example, the leftmost island is of size 5. So this is the maximum, and this has only 3 people. So this is the minimum island. Okay. This was all there was to the problem, right? So yep. So in this example, for example, so 1 and 2 form an island. 2 and 5 have a breakpoint because they are, the difference is more than 2, and then 5, 6, 7 is again an island because the difference is less than 2. So this is one island. This is one island. So the smaller island is of size 2. Here it's size 2. Larger is of size 3. So it's size 3. In the previous example, everything is like it's one island, right? There is no breakpoints. So the smallest and the largest, like there is one island only. So it's both the smallest and the largest. So hence 3 and 3. And similarly, the first example. Okay. So mostly everyone solved this problem, I guess. Even the second problem. Okay. So in the second problem, we have 26 viruses. Yep. So these are just A corona, B corona, C corona, and so on. But effectively, the only thing that matters is the first character, right? So what are we given? We are also given a string S of length n. There are n people. for each valid I, right, that is from I from 0 to n minus 1 if it's 0 indexed, or 1 to n if it's 1 indexed, the ith person is infected by exactly one type of virus named SI corona. SI corona. So the corona part is again not relevant. It is just the virus name is just SI. So it's just identified by a character, right? So we have Q queries. The definition of a query is rather long. So effectively what it wants is we have to kind of distribute all the people into C isolation centers, and there is a large pending queue, like a large buffer region. So we want to maximize the number of people that we can put in any one of the isolation centers. The only thing, the only restriction here is if two people are in the same isolation center, they must have the same kind of disease. So C is 10 to the, so C is quite high. N and Q are also quite high, but doesn't really matter. So the string is given in the at first only, right? So I'll not go into the subtask 10 case. It's some kind of brute force, I guess. So we will directly jump to how to solve the whole problem. That is, so each person has some kind of virus, right? Now, if two person have say virus of type A, then both are equivalent, right? So we only need to keep track of how many people have the virus A. It does not matter who has the virus A, and like if two different people have the virus, I mean, it doesn't really matter, right? So we just have to keep track of how many people have virus A, similarly how many people have virus B, how many people have virus C. So we will get some kind of a frequency array, correct? So for each of the 26 virus, so let's say for A, we know that 5 people have this virus. For B, we know that let's say 10 people have this virus. For C, uh, let's say 7 people have this virus. Okay, and so on for D, E, F, G. Now, when we are given a query, so we are given some C. So one thing to note is that the fact that C can be up to 10 to the power 9 does, like, any C greater than 27 does not really matter, right? Because if C is 26, so there are 26 possible characters, right? So if C is 26, then for each isolation center, so let's say these are the isolation centers, we can assign to each isolation center a particular character. So let's say this is character A, rather character virus, both are equivalent, right? And now we say that the isolation center with character A, everyone who has virus A will go to this isolation center, right? And we will effectively have nothing in the pending queue, because there are 26 characters, there are 26 isolation centers. Everyone will go to their respective isolation centers. So what if there are less than 26 characters, right? So one thing, 27 to 10 to the power 9 does not really matter if it's above 26. Second, what if it's less than 26? Let's say it's 2. There are, so in this example, let's say instead of 26 we had 3 types of diseases, and we had 2 isolation centers. So what will we do? So let's say we have one isolation center like this, one like this. So it makes sense that every isolation center will have a particular type of virus treated, right? So this isolation center, let's say, will have the virus A treated, and this will have the virus C treated. So everyone who has virus A should, like, obviously go to the isolation center marked with virus A, right? Everything with virus C will want to go to wider, like, position C. Uh, so the optimal strategy here, like if you think about it in kind of a greedy way, we want to put as many people as we want as we can to at least one of the isolation centers. Second, we also concluded that each isolation center will treat at like exactly one kind of corona disease. So the strain of the virus which has the largest uh, number of people getting affected by it, we will want. So yeah, so as I was saying, if you have the virus affecting the largest number of people, they should be assigned to a isolation center preferentially, right? So here B will first get assigned to a isolation center, that is A. Sorry, I already drew that line. Yeah. So here first B will get assigned to one isolation center, right? And next we see that who is the second largest one, like the strain which is affecting the second most largest population. So here it is C. So C will get assigned to an isolation center. We have only two isolation centers, right? We already assigned two of them. So the rest of the people who are left, they will go to the pending queue. So again, this was the full problem. You just had to find if C was greater than 26, then everyone gets assigned. If C is less than 26, then assign the C greatest, like the viruses with the C greatest number of population. So here in this case, the two greatest are B and C, since 5 is less than 7 and 10. Yeah. So does anyone have any doubts in this problem? Only one person can be allowed with the same virus in the center? No, every like multiple people can be allowed. These should be clear from reading the question. So, okay, so let's move on to the next problem. So I'll first discuss Chef and Bitwise product because at least to me it's a bit easier than triple sort actually, and because triple sort and sorting vases are both related to permutations, so I will try to discuss them together because there is one concept that is needed in both of them, right? So Chef and Bitwise product. What do we do here? So there's a function given f x y z. It's basically x and z into y and z. So if we are given x and y, we want to find the value of z, and there are certain restrictions on the value of z. It has to be greater than L, it has to be lesser than R, right? So, yeah. And then we have to just answer multiple queries where we are given x and y, right? So the number of queries, or rather the number of test cases, both the same here, is rather large. X and Y are also rather large. Someone is saying that he did not get the problem state right. Is it so? Let me just check once so that. Um, I did get it correct, right? You are packing multiple people into the same isolation center such that all of them have the same kind of virus. Yeah, so it should have been. Okay. So let's say there are no restrictions. So that's the first subtask, right? There are no restrictions on L. There are so R. So there is this restriction that R is greater than equal to 2 into max of X and Y, but this is effectively we don't have any restrictions on Z. So why is this so? Let's say X and Y were 0, 1. So I'll denote the numbers in their binary representations. The first bit is the like this is representative of 2 to the power 0. This is the first bit, and I go from left to right. Actually, rather I'll do the opposite in this case. I think I'll go from right to left. So this is the most significant bit. The first bit is the most significant bit, and then we move on to the least significant bit. So let's say that we have something like this. This is x, and similarly y is equal to, let's say, 0, 0, 0, 1, 0, 1, right? So one thing to note is, so how do we approach this problem? So we have to find a z, such that x and z into y and z is maximized, right? So let's say there is a set bit in z and there is a set bit in x. So if both of the corresponding bits, so let's say z is this, so the second most important bit is set in both. The third, this bit is not set here. So effectively x and Z for this set of this example is 0, 1, 0, 0, 0, right? And similarly, y and Z is equal to 0, 0, 1, 0, 0. And then we take the product of these two. So let's denote this by A, let's denote this by B. We report A into B. So our best case scenario, what we want to do is, what we want to think about is, how do I maximize both A and B? So if I have a solution where, so let's say we have two possible values of A1 and like A and B, right? Rather, let's denote this by A2, B2. When do we say that this is definitely better than A1, B1? When both A1 is less than A2 and B1 is less than B2, right? Then definitely this product is greater. So if we can better both A and B, then we will be getting a better solution, right? So the thing is, for Z, how do we choose an optimal Z such that both A and B are together maximized? So in the first condition, we are just given that Z has to be lesser than 1, 0, 0, 0, 0, something like this, right? This is not the exact thing. Z has to be lesser than this actually, but even let's say it just has to be lesser than this. Now, if Z has the first bit set and the first bit in X and Y are both not set, right? Then there's no point in setting this first bit, right? If it is 0 or if it is 1, it does not really matter. So in any case, the first will not be set. So it will always be lesser than the R value given. So if in the first subtask, Z will always be less than equal to R, like any meaningful Z, right? Like there's no point setting the first bit of Z to 1 anyway. So next, we want to say that we want to somehow, so the best case scenario here is if A is equal to X, correct? A cannot be greater than X anyway, because like you are doing X and something, so you cannot have more set bits than A. So the best case scenario that you can hope for is A is equal to X, and similarly the best case scenario for Y that you can hope for, sorry, for B that you can hope for is B is equal to Y. So can we achieve these two? If there are no restrictions on Z, can we achieve these two? Okay, so I'll try to explain again why there is no restriction on Z in the first subtask. In the examples that we had taken, X equal to 0, 1, 0, 0, 1 and Y equal to 0, 0, 1, 0, 1. What is the value of R actually in this case? It's just 1, 0, 0, 1, 0, right? So multiplication by 2, we are effectively doing a multiplication by 2, right? So multiplication by 2 is basically shifting everything once to the left. Now, let's say the highest bit in X and Y, like in any case, is like you have a 0 bit. Let's say you append a 0 bit in front of the highest bit, right? So yeah, so R will have the 1 bits, like the first bit set in R is greater than the highest bit set in X and set in Y, right? So in the first subtask, there is effectively no restriction on Z because Z will always be less than R. The first bit in Z, so what is the scenario when Z is greater than equal to R, or rather greater than R? When, so this will only happen when the first bit set in Z is at least is same as first bit set in R, right? Since there is no point setting the first bit that was set in R in Z. So if Z is something like 1, 0, 0, 1, 0, 1, 1, this is same as setting Z to 00011 because the first bit won't get ANDed to anything in X and Y. Hence, there is no restrictions. So moving on, we have to so the best case scenario that we can think of is A is equal to X and B is equal to Y, right? This is the best case scenario. We cannot get an A that is greater than X, or we cannot get a B that is greater than Y, right? So can we achieve that? Well, the simplest solution, and I'm not sure how to give you an intuition into this, is just setting A is equal to X. I mean, setting Z equal to X or Y. Okay, so this is the OR operator, rather a single OR. So this will mean that every bit that is less than every bit that is set in both X or it is set in Y, our Z will contain that bit, right? So when I do an AND again, like when I do this X and Z step, every bit that was set in X is by definition also set in Z. So A will effectively become X, right? So for our example, we will have something like this. So for our example, the Z will be like this and X will be just this, right? And Y will be this. So every bit that is also set in Y is also set in Z because we defined Z as that. Every bit that is set in either X or Y, we put in Z. Now, again, this will not go beyond R because R has a set bit that is more significant than the highest, like the most significant bit in X or Y, right? Because if the MSB of X is equal to the, let's say it has the 5th bit set, right? Then MSB of R will have the 6th bit set always, right? But whatever value we have in Z, the MSB of Z will be will be equal to 5, right? So since like we are taking X as the greater value in X and Y, the other case is analogous. So since the highest set bit in any one of the numbers is 5, the highest set bit in Z will also be the same as the highest set bit in whatever number there is. But the highest set bit in R is 6. That's why R will always be greater than Z. Hopefully it makes sense now. Okay. So this was the first subtask. We just put Z equal to X and X or Y, and then we compute fxyz. Now we have a restriction on R, right? We don't have a restriction on L. We just have a restriction on R that our Z value should be lesser than this, some given R value. Okay. And that R value need not be greater than equal to 2 into xy, right? So if X and Y were these, so let me go up to X and Y. So if X and Y were like this, our R could very well be 0, 0, 1, 0, 0, or rather 1, 1, 1, something like this. It can be less than X also. So how do we tackle this? Well, we do a brute force, right? So the brute force is so we are considering the prefixes of this number as going from left to right. Note that this is not be like LSB to MSB. This is most significant bit to least significant bit. So we are when we are going from left to right, we are moving from most significant to the least significant, right? So let's say Z and R. So let's say R is in our case 0, 0, 1, 1, 1, right? So let's say that okay, the first 3 bits are same, or rather the first 2 bits are same in R and Z. So we know that Z has to start with, so this is R. So we know that Z has to start with 0, 0, correct? And I say that this is the longest common prefix for R and Z. Yeah. So this is the longest common prefix between R and Z. That means the next character must be different. Now Z cannot be greater than R, correct? So what if the two characters are different? One possible scenario is r equal to 0, z equal to 1. Another possible scenario is r equal to 1, z equal to 0. Right? These are the only two possibilities if r and z has to be different at the next character, right? If it was same, then we would have extended our longest common prefix, but we have already said that the longest common prefix is 2. That is our brute force like condition here. So since r is 1, we have to put a 0. Now note that if r was 0 here, then this would not have been a valid case, because we cannot put z as 1 here, right? Because then z will be greater than r. That is not what we are trying to do. We are trying to have z less than r. So the only place where we can actually kind of make a valid break from rather a valid brute force checking is when r is 1 and then we put z to 0, and then for the rest of the characters we have free control. We can put it to 0, we can put it to 1, we can do anything, right? So for these last two characters, the optimal thing to do is just take the last two characters of x and y, right? So let's say y was this. Actually, I'm just changing my example a bit. So take the last two characters of x, the last two characters of y, and then OR them together, like in our previous example where we showed how ORing two things and then doing calculating f, x, y, z is the best case scenario. Same here. If we OR them together, we will get 1 and 1 in our last two places, right? Okay, so let me just reiterate on what I told. We are so z and r will have, so let's say we have some magical optimal z. Okay, this is this z0, or rather z optimal. So z optimal and r will have some longest common prefix, right? So I don't know what is the longest common prefix between z optimal and r, but that's why I'm trying to brute force that. Oh, I'm saying that, okay, let's say if 3 was the longest common prefix. So what I'm trying to do here is I'm trying to say that, okay, let's say longest common prefix was 3. Then what is the best f, x, y, z we can get? Or let's say, what if it was 4, then what is the best f, x, y, z that we can get? Similarly for 5, we want to get the best f, x, y, z, right? So now after calculating all of them for, like, say from 0, 1, 2, so on up till the maximum number of bits in x and y, so max bits, we take the maximum value of all these f, x, y, z that we had got till now. So this, if this was f1, this was f2, this was f3, we take the max of f1, f2, f3. This is what we are effectively trying to do. Now if I say that 3 is, let's say 3 is the longest common prefix, I want to calculate the best f, x, y, z, right? So I am basically trying to understand what is the z value that will maximize f, x, y, z if 3 is the longest common prefix. So in our example, let's say r was this, and I said that, or rather, let's calculate this for 2 first, because I was doing that only. Yeah, so let's calculate this for 2. So the first two characters of z and r and z are the same. Okay, that is what we are trying to calculate. And then the next character, we have to ensure that r is 1 and then z is 0. If r was 0 here, then the best, like this case is then irrelevant, right? I mean, you cannot have a longest common prefix of 2, then you will always have a longest common prefix of either 1, or not even 1 here, of 0, of 3, right? Because if you say that I have a longest common prefix of 2, then that implies that the third character must be different. But if r is 0, I cannot really put 1 here, because then z will be greater than r. Hence, I have to put 0. Hence, 2 is not the longest common prefix. 3 is actually the longest common prefix. Anyway, so let's say r was 1 here. We got 0. And then the rest of the two characters in z, we can put 0, 1. We can put anything, because z is already less than r. It is already already strictly less than R, right? It's not equal to, it's strictly less than R whenever we differ the bit between R and Z. And then we can do anything with the rest of the bits. So claim is that you just take the odd value of the last 2 bits in X and the last 2 bits in Y. So you take the odd values between this and this. So the odd for them is 1, 1, right? That's why you have a 1, 1 here. And this will maximize fx, y, z, right? So yeah, so z is less than equal. So z, whenever I differ a bit like from the left, I guarantee that z is always less than r, right? Because like the most significant bit in this number is 1. Like in the third place, this is the third place here is 0, and everything to the left is similar to r only. So the first place where it differs, that's what matters. So hopefully the second subtask is clear as well. Now for the last subtask, we have a lower bound as well, right? But we do a similar kind of processing. We say that, so when we have L and R, when we have both, then we have some longest common prefix of L and R, right? So let's say R is 0, 1, 1, 0, 0, 1, 0, and L is 0, 1, 1, 0. Let's add 0 here. 0, something like this. So this is R and this is L. Yeah. Okay, by the way, one question someone asked, L, we have to calculate Z inclusive of L and R, right? So yeah, so before doing this, you check for R and for L individually, like the boundary conditions you check individually. And then what I am trying to do is I am trying to find a Z that is strictly less than R and strictly greater than L. Okay, you check the boundary conditions individually. So let's say L and R are like this. So the longest common prefix between R and L is something like this, right? So the first 4 characters are same in L and R, and this implies that the second, like the first 4 characters in Z must also be equal to. So the first 4 characters must also be equal to Z 0, 1, 1, 0, right? Now for the next characters, just 1 second. So now, so the first 4 characters are already fixed. So let's just assume that we deleted these. Okay. So now again, we do something like in the previous subtask where we try to find the maximum, what do I say? The maximum prefix with Z and R in this reduced condition. So the first 4 characters of Z was also like this, and then we need to fill the remaining 3 places, right? So let's just ignore the fixed characters as it will make our life easier. And now let's say that we have a prefix of R and Z that is fixed. Okay. So we are again brute forcing on the prefix of R and Z that are equal. So let's say we say that the first, like the longest common prefix of R and Z equal to 1, right? So we again force some of the characters of Z, correct? We force some of the characters of Z to be, like the first character of Z to be 1. We force the next character of Z to be equal to 0. And whenever we do this, we effectively know that Z will always be greater than L. Why? Because the longest common prefix between L and R, the first character after that longest common prefix, so our LCP between L and R were 0, 1, 1, 0, 0, 1, 1, 0. The first character after this would have been R is equal to 1 and L is equal to 0. That is the only possible scenario, right? We cannot have L equal to this character of L equal to 1 and this of R to be 0, because then L is greater than R. So we always have the first character of R to be 1 after the longest count prefix. And similarly for L, after the longest count prefix, we have the first character to be 0. So, okay, so as I was saying, let's just ignore this longest count prefix because it's same for Z also. Now I am saying that, okay, let me say that after that longest count prefix, we have another stretch of characters, another few characters which are same in Z and R. So here I said that this longest count prefix between R and Z is equal to 1. Okay, so this is after the after attaching the LCP of L to Z. This basically means that after I set Z to 0, 1, 1, 0, I am doing everything now after this. We have already done this, right? This has to be. We cannot do anything here. So after this, if I say that the LCP of R and Z is 1 after doing that, then that means the first character of Z must be 1, the second character must be 0. I mean, the second character of R must be 1 and the second character of Z must be 0. And the rest of the characters, again, we can put anything. Why? And why will this always be greater than L? Because whenever we said that the first character is same as R, we already said that the Z is greater than L. Because see, L has 0 here, right? R has 1 here. Whenever I said that the first character of Z is same as R, I automatically ensure that Z will always be greater than L. And so we can, so the first, so if we said that LCP is 1, we have the first character fixed. The second character is also kind of fixed because R has to be 1 in that character and Z has to be 0. And the rest of the characters, we just do that odd thing again. So whatever characters are left, we take the odd value of those remaining characters from both X and Y, and we just place them there. Now, what if LCP of R and Z is 0? That means it is starting with 0, right? It is, so now I am ensuring that Z is always less than R. So in the previous case, we had ensured that Z is always greater than L. In this case, we are ensuring Z is always lesser than R. Now we say that how many characters of Z and L are same, like what is the LCP between L and Z. So here now, this is case 1, rather case 1 was LCP of R and Z greater than 0, and case 2 is LCP of R and Z equal to 0, and then we try to fix LCP of L and Z, right? So it's a very similar case. If we say that the LCP of L and Z is 1, then the first character of L and Z should be same, that is 0. The next character L is 0, then Z must have 1 in this place, and the rest of the characters you can put anything because you already ensured that it is greater than L, right? Okay, so okay, I'll just try to read off the chats and see what all doubts you have. A dot B to be max A should be equal to B. Uh, A should be equal to B. You cannot really do A equal to B. Your best case scenario is if A is equal to X and B equal to Y, not A equal to B. That is not what we are trying to achieve. We are trying to achieve maximum value for both A and B. Because when there are no constraints, we can achieve both together. Um, for second task, Z will be 0, 1, 0, 0, 1, 1, 0. I'm not entirely sure. Why should it be 0, 0, 0, 1, 1, 0? It has to be, it has to differ from R at the, if LCP was 3, then it has to differ from R at the 4th place, right? So if R was 1 at the 4th place, it has to be 0. If R was 0 at the 4th place, then we just skip over that case, because if R is 0, we obviously cannot set Z to 1 at that index because then Z will be greater than R. Nor can we set Z to 0 because then the longest one prefix is not 3 anymore, it's 4. So in that case, we can skip LCP R and Z. Okay, so I'll try explaining this in short once again. Let's say the thing is 0110, L is 0110. I'm not currently caring about what the values of X and Y are. I'm just trying to show like how do we put Z into the bounds correctly. So here LCP of R and L is equal to, the first four characters are same, right? So LCP is 4. So we know that the first four characters of Z must also be 0110. You cannot really escape that. You cannot change it. Correct? Okay. Now I am saying, now that you have fixed the first four characters, forget about them. Let's try to fix the remaining characters, remaining three characters in this scenario, for example. What are the remaining three characters? So just for clarity, I am just removing all these. Okay, LCPRL not needed. I'm just removing the first four characters. Yep. So now I am saying that forget about that LCP L and R equal to 4. We already have accounted for that. Now say that LCP of R and Z is equal to 1 or greater than equal to 1. What does that mean? It means that the first character is same as R. Okay. Whenever I say that the first character is same as R, I already ensure that Z is always greater than L, because the first character in L was not same as R. It was 0, R was 1. If Z is equal to 1 in this character, then it will always be greater than L, right? Because from left to right, we are going from most significant bit to least significant bit, correct? Now, the next bit is also like we can also correctly determine the next bit as well from R, just as we did in the subtask 2. So we can do the next bit as well, and the remaining bits we can just take the odd of the last few bits, right? If we have 3 bits remaining after this, we take the odd of the last 3 bits of X and the last 3 bits of Y, just like due to the logic of the first subtask. Now this is when I am saying that Z and R have a few similar bits. When I am saying that the LCP of Z and R is equal to 0, then that means the first character of Z is equal to 0, right? So it is already less than R. So now I am saying that, okay, if this is the case, then fix the longest common prefix between L and Z. You fix the longest common prefix, and then the next character is also fixed due to the logic of subtask 2. The rest of the characters are also fixed, like not fixed, I mean you can determine them by taking OR using logic of subtask 1, and you are always ensuring that L, like the Z value, is greater than L, because you are choosing a particular prefix, and it is always less than R, because R had 1 in the first position, you have 0 in the first position, since common prefix between R and Z is 0. So hopefully this is clear, right? The main idea in this problem was we fix a certain number of most significant bits from we fix a certain prefix of most significant bits. We say that the next bit is different. We say that the next bit is different, and then the rest of the bits we can just greedily put by putting everything as 1. Right. I mean, even if you don't do odd, you can just put everything as 1. I mean, that's the best case scenario, right? When you take AND, if there was a 0, then no problem, it will get a 0. If there was a 1, you will get a 1. So yeah. Okay. So let's now move on to the last two problems, and first is this triple sort problem. So this problem is based on permutations. So quick things about permutations that I want to just mention. Permutations, a very common technique to think about permutations is thinking about cycles. Okay, so let's say this is our array. So instead of, so let me draw a beautiful array. So the numbers here, let's say this is, we will just randomly do a permutation 1, 5, 6, 2, 4, oops, 4, 3, and what do we have left? Okay, let's put 7 here and 3. Okay, so this is our array. Now, what do I mean by permutations? So ideally, what should have happened? Ideally, we should have 1 here, like, which is the identity permutation, 2 here, 3 here, 4 here, 5 here, 6 and 7, right? So what we can do is we can think about it key, like consider this as nodes maybe, and then you add edges. So the value at the second position is 5, right? So you add an edge from 2 to the 5th position. Okay, so this effectively represents that the number that was here, so which is 5, it needs to travel along this edge to its actual place in the identity permutation, right? So it needs to travel to 5th position. Now, from what is there in the 5th position? The number 4. So where does 4 need to travel? Here, right? So we will add an edge here. Now the number here is 2. So where does 2 need to travel? 2 needs to travel here. See how we get a nice circle, rather a cycle. So 5 goes to 4, 4 goes to 2, 2 goes to 5. Similarly, for 1, 1 is already in the correct place, so it's just a self cycle in some sense. For 3, 3 needs to go to, like, the number here is 6, 6 needs to go here. So let me draw in a different color. 6 wants to go here. The number here is 7, so this actually wants to go here. And the number here is 3, so 3 actually wants to go back to 6. Okay, so again, this is another cycle. So any permutation has these sorts of cyclic decompositions. Okay, these are very fundamental to permutations. Every permutation is basically a composition of these cyclic decompositions. Yeah, composition of decompositions. Nice. So you can break any permutation. So another thing to note is that these cycles will always be disjoint, because every node will always lead, like, have only one single edge to some other node, and you are just following the edges, right? So just give some thought to it. It's kind of easy to prove that the cycles will be disjoint, and you will have basically all these cycles consisting of various edges. And if you do a cyclic shift over all the elements, so cycle is basically a cyclic shift, right? You want to place the 4 to this position, you want to take this element to this position, you want to take this element back to this position, right? And it can be 3 cycles, then cycles can be larger than 3 cycles, stuff like that. So this is one thing. Second thing is the concept of inversions, right? So inversion is basically, say you have so let me go to a text block, something like here. Hopefully everyone can see that text. Like, if so, just say a yes in the chat so that if you can see. Yeah. So let's say we have a permutation like 1, 3, 2, 4. So what is the inversion count here? Inversions are basically all pairs I and j such that I is I is less than j, correct? But pi is greater than pj. So here, for example, 3 and 2 form an inversion, because 2 should be actually before 3 in the identity permutation, but it's not here, right? So how many inversions there are? It's basically number of these pairs. These pairs are unordered pairs, okay? So let's say if our example was 4 and 2, something like this. So number of inversions here is there are how many inversion pairs? 1 and 3 is fine, 1 and 4 is fine, 1 and 2 is fine, 2 and 3 is an inversion pair, right? So 2 comma 3 is an inversion pair. 2 comma 4 is an inversion pair. 3 comma 4 is not an inversion pair, so it's fine. So we have two inversions, right? So I say that a permutation is even if number of inversions is even and permutation is odd if number of inversions is odd. Okay. Okay. So these two things are should be. Oh, okay. Another thing, when we swap two numbers, so let's say we swapped 3 and 2, so it became like this. Our parity of inversion, like our parity of the permutation changes. So if the permutation was even, then we do a swap, then the permutation will become odd. I'm not, note that I'm not saying how many inversions will it will have now. I'm just saying that if it was even first, it will become odd now after one swap. So after one swap, it becomes permutation is odd, and similarly vice versa. Okay, if the permutation was odd, the permutation after a swap will become even. Okay. This fact you can prove yourself. The proof is, I think, also given in the editorial. Let me just check once. Yeah, so the proof is given here. It can be shown that the parity of the permutation changes. I will not go over the proof here. You can see it in the editorial itself. Yeah, so these are kind of the basics that we will need to know to handle this problem. So, okay, I think actually we need one more thing. So remember how we had cycles, right? Cycles was something like 1, 3, 5, 7, 5, 6. So what does this cycle mean? It means that 1 actually needs to go to the position 3, 3 needs to go to the, like, whatever was in 1 needs to go to whatever was in, like, to position 3, whatever was in position 3 needs to go to position 5, whatever was in 5 needs to go to 6, and whatever was in 6 needs to go to 1. Okay, so it's kind of like the cycle traversal. Whatever was in position 3, which was 6, it needs to go to position 6, right? Whatever was in 6, which was 7, it needs to go to position 7. Whatever was in 7, it needs to go to 3. So the permutation, like the cycles here would be, so the cycles here would be, well, 1 is a cycle. Oops, sorry. So 1 is a cycle. 2, what is this position? 5, 4 is a cycle, right? So 2 needs to go to 5, 5 to 4, and 4 to 2. So note that I'm not saying 2 itself needs to go to 5. Whatever was there at position 2 needs to go to the position 5. And then we have another cycle, 3, from 3 I go to 6, and from 6 I go to 7. So, and it's actually 2, 5, 4, 2, right? Because whatever was in there in 4 also needs to go to 2, but I will represent these as 3 elements, like not have the repeating first and last element. So claim is, if you have this sort of a cycle, so what is a swap? Swap is basically a 2 cycle, right? Swap is basically something like this, right? So in whatever what you do in swap is, you take an element from, so I am not taking this example. This is a wrong example for showing a swap, but swap is basically you take this item to this position and you take whatever was in this position to this position, right? So this is basically a swap. Now, what is cool about permutations is you can take any cycle and list them as a, like a combination of swaps. So how does that work? So if you had this sort of a 4 cycle, this is effectively the same as 1, 3. Like when I write the cycles side by side, it means I do this swap, then this swap, then this swap, then this swap. So 1, 3, 1, 5, 1, 6. So if you have a cycle of length 4, cycle, if cycle length is s, then you need s minus 1 swaps to like move around everything in, according to the cycle, and kind of uh, what should we call it, destroy the cycle. Like, yeah, I mean everything gets back to its own like original place, as in the identity permutation. So this is true. So you can so like notice the pattern here. We are taking the first element and then we are like attaching the adjacent elements to it one by one, right? So why is this true? Let's take a graphical example. So let's say our nodes were like this. Let's say our nodes were like this and our edges were in a cycle. Oops, 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 oops. So our edges went in this cyclic order, right? And so on. Now, this is 1, this is 2, this is 3, and so on, right? So when you swap 1 and 2, so what does that mean? That means this position was actually 2, right? So that means this position was actually 2 and you take it to its original place. So whatever was here in 3, whatever was here in 2, it's actually, let's denote it by 3, and like so on, like it's 4. So the nodes are basically the positions. Whatever is in the node is basically the actual value that is present in the array in that position. So this corresponds. So I'll also draw the corresponding array here just for clarity. 5, 6, 7, and 1. So the array that this represents is the following. Uh, the array it represents is 2, 3, 4, 5, 6, 7, 1, right? So, and this is the array, right? Very simple cycle. Yeah, so basically everything needs to like get cyclically shifted once to the right, but it's still a permutation. It like the cycle still still holds, right? So 2 wants to get to 2, 3 wants to get to the position 3, 4 wants to get to position 4, and so on. So when I talk about these swaps, so how are these equivalent to like swapping with the first item always? Why is this true? After the first swap, what will happen is you will have 3 here. Let me take a different color. You will have 3 here and 2 here, correct? So 2 is now in the correct position. Now you swap these two items, right? So now your 3 will go to here. So you will now have 3 here and 4 in this first position, correct? So you will now have 4 here. 3 is now in the correct position. Now you have this thing, 2 and 4. Now your 4 goes to this fourth position as was correct. So you have 4. And your 3, let's rather, sorry, this is 5. So 5 now comes to the head, like the first position, right? Similarly, you when you do this swap, so it's like you are taking one element and you are swapping it to the next element. Whatever was there in the place that you were swapping, that was misplaced, right? So you take it to the first position, and it's kind of like you are saying that okay, you are in the first position. That means next time you will get placed in your correct position, and you are kind of exchanging it for something that is also not in its correct position. So uh, like in that case kind of sense, right? I mean, obviously this is a like this example also kind of shows what I'm trying to say, but if you want to think about it in that way, like you are taking something that is not fixed, you are taking it to the first position, and then in the next iteration you are putting it back in the correct position. right? So in this way, one cycle, like shifting everything along one cycle, is effectively doing these swaps individually. Now let's get back to our original problem, right? Here we have these three triple sort. So here we have like shift ijk, something like that. I'm saying this correctly, right? So let's say there's this function shift ijk. Okay, so shift ijk. What does shift ijk effectively do? Shift ijk is effectively swapping ij and then swap ij and then swap I comma k, right? Again, the same logic. You keep the first element fixed and kind of swap all the other elements with the first element. So the first question is the array triple sortable? Like, can it be actually sorted using these swaps? Now, thing is, every shift operation. So one thing is for sure, right? Because like that we can sort any array using swaps. Like bubble sort is based on that, I think, right? So now the problem is we are not doing individual swaps here. We are doing a shift operation, which is actually a combination of two swaps. So remember how every swap changed the parity of the permutation? What is the parity of identity permutation? It's like even, right? Like identity permutation has zero inversions, right? Hence, it has even parity. Now, if your original permutation that's given in the question has odd parity, if your permutation has odd parity, we can never reach an even permutation using shift operations, right? Because every shift operation does two swaps. Each swap changes the parity. So after a shift operation, your parity remains the same, correct? So hence parity remains the same. So if you first you check that if permutation has odd parity, then directly like return -1. Like it's not possible, right? If it has even parity, then how do we actually get a solution? Okay, so let's get back to the permutation cycles. So let's get back to the permutation cycles. Yeah. Yes. So you have, so there can be two types of cycles, right? There can be cycles of even length, there can be cycles of odd length. Now notice here that if a cycle has even length, that is 4, you need 3 swaps, correct? So instead of saying that a cycle has even length when there are 4 elements, for the sake of convenience, I'll say the cycle has even length if we need 4 swaps to correct the cycle. So in this case, this is actually an like odd cycle in my terminology. Odd cycle means we need odd number of swaps. Now, what we want to do is, so what our strategy should be is fix every cycle like separately. There is no reason to kind of mix two cycles, right? Why would you want to mix? You can fix each cycle individually using S, like if the cycle length. So if, so there are two cases, right? If cycle is odd, has even length, let's say it needs S swaps. Note that I am saying S swaps. It means that the cycle has S plus 1 elements. If it needs S swaps and S is even, then we can just combine each two consecutive swaps, right? How? So let's say the cycle was A, B, C, D, E. Then we have A comma B. The swaps are A comma B, A comma C, A comma D, A comma E, right? So we can represent them as shift. So remember how shift ijk is essentially ij and like swap ij and swap ik. So we can essentially represent them as shift A, B, C, right? And shift ABC is shifted and then A, D, E seems correct. So if we had to do S swaps, we can just do S by 2 shifts. This much should be clear, right? The main part is, what if there are odd length cycles? So remember how I defined odd length cycles to be where there are odd number of swaps. So what is an example for that? Let's say A, B, C, D. So here the problem is the swaps that you need are A comma B, A comma C, A comma D. Now you can do something like shift A, B, C. Wait, oops. A, B, C. But then what do you do with this additional swap? A comma D, like nothing you can do, kind of, right? I mean, you cannot really combine it with a shift operation. So what do you do? This is another tricky part of the problem. You have to observe that firstly, so there cannot be even number of odd length cycles because that messes up your parity. Because see, uh, sorry, I said the completely opposite thing. There cannot be odd number of odd length cycles, right? Because odd into odd, let's say you have 5 odd length cycles, then the cycle lengths are, let's say, 1, 3, 5, 7, 9, something like that, like any odd numbers. Your sum of them will also be odd, right? So the total number of swaps will also be odd. But this implies that the parity is also odd. Correct. So that is why you cannot have a cycle, rather you cannot have you cannot have odd number of odd length cycles. You always have even number of odd length cycles. Just to clarify, if there were odd number of odd length cycles, then it would have like been caught in this part where we checked if the permutation has odd parity or not, right? So we are confirmed that there are even number of odd length cycles. Now in every odd length cycle, we will have this one extra swap that we cannot account for. The rest of the swaps we can do using shifts. There's this one swap that we cannot do using a shift, correct? So what do I do then? Well, thing is, what you can do is you can combine this remaining shift with the shift with like this remaining swap operation with the swap operation of the next odd cycle. Okay, so suppose the next odd cycle was something like, so notice that the cycles are separate, right? So you do not have common elements. So let's say the next cycle was x, y, z, rather w, x, y, z. So the swaps here are wx, wy, and wz. So now I'm saying that this will also have a remaining swap, correct? This will also have a remaining swap. Now you can kind of like, and this part also you have to kind of think about on like yourself. I mean, it's not a common trick. Absolutely, it's at least to the best of my knowledge, it's not a common trick. It's a problem specific trick. If there are 4 indexes, and I think I should refer to the editorial here because like, it's given well. So it's basically observation 2. Two regular swaps ij and kl such that IJKL are pairwise distinct. This is the keyword here because we are combining 2 swaps from different cycles together, like the remaining swaps of the different cycles together. So IJKL are all pairwise distinct. If you have IJKL that are pairwise distinct, then you can combine them together using two shifts, right? So IJL and KLI. So you have to kind of come up with this by hand mostly, and then there's a sort of an example given here for clarity. But yeah, so this is the key part of the problem. If there are remaining swaps, you combine them together using two shifts. So previously we were combining two swaps into one shift. Now we are combining two swaps into two shifts. So this is not really worse, because like how many cycles, independent cycles can you have actually? You cannot have more than n by 2 independent cycles, right? And when you are combining the swaps for the odd cycles, for all the independent odd cycles, for every swap you are effectively using one shift, right? So in some sense you are using one swap and one shift, but there can be only n by 2 swaps, so you again use at most n by 2 shifts. So that was all, like that was all there was to it. You just find out the cyclic decomposition. So what all did we do? We found out all the cyclic decompositions. We broke them down into these swaps, where every swap has the first same like the first element same. We combined like the two consecutive swaps into one shift operation for all the even cycles, and for the odd cycles we combined as long as we could. There was something remaining, we combined the remaining thing with the start of the next cycle. Okay, so if this swap was remaining, we combine it with ad and y w's x. We have to use two shifts for that, obviously, but and then we kind of continue doing the remaining swaps. Like as long as there are two consecutive swaps, we combine them using one shift. And if there are four different elements, we do two shifts. Now one thing to note here is there is a certain way to process the shifts, and this might have come naturally. So the most natural thing that we want to do is, okay, let's process all the even swaps, like even cycles first. We will, and then after that we will process the odd cycles, right? So in that case you will get AC. There was like, however, if you kind of not process in that order, you would have not got the third subtask correct, I think. uh, and also it's a non-trivial proof is given here um, in proof 3, I guess, where it shows that okay, proof 2 and proof 3, where it shows that how one order processing is basically it bounds by 2n by 3, and in another order it's bounded by n by 2. But to me it seems kind of intuitive that we will want to do the even cycles first and then the odd cycles, rather cycles with even number of swaps first with the first, and then the cycles with odd number of swaps. But still it's given here for like if someone wanted the proof. So I will not go over the proof today because like it's not short. So yeah, but check out the editorial for the proof. Okay, so triple sort, we are done with 4 problems. The last problem, sorting vases. So this problem is again based on permutations, and we will be needing more or less the only concept that we will be needing is the permutation cycle concept, right? So in this problem, it is given that you can do swaps uh, in order to achieve. So you are given a permutation and you want to restore the, like make it the identity permutation. What you can do is you can swap two vases in 1 minute, and then there are m pairs given. So for those specific m pairs, you don't have to do a swap. Okay, like I mean, in the sense that even if you do a swap, you do not incur a cost. You can do those swaps freely. Okay, so to give a visual representation, so you have these nodes. So I am denoting each index by a node. So let's say it is given that you can swap between these two and swap between these two freely, and for any other swap you need to pay a cost. Okay, so what is the first observation that we can make? It's that if there are two indexes, like if there are two possible pairs of valid swaps. So let me just give some space here. So if there are two free swaps, let's say A and B, and let's say B and C, then we can also do the free swap A and C, right? Like I can swap from A to B, B to C. It's effectively A, B, C. Like you can swap between anything, like, right? You can rearrange any of the items. So it's kind of like you have a connected components of places. Inside the connected component, you can rearrange however you want without paying any cost. Now, if you want to rearrange between two different connected components, you have to pay the number of swaps you do, you have to pay those many, like that much cost. So if you do k swaps between different components, you have to pay k in cost, right? So just to like show what I'm saying, okay, this. So in these cases, it kind of helps to think of the array as a graph where each node is the index or index of the array, and the graph, like, okay, at least for now. So now the free swaps I'm denoting by red. So let's say I have free, oops, sorry. I have a free swap like this. I have a free swap like this. I have a free swap like this. Free swap like this. And then I have, so these components, right? So these nodes, I am calling this a connected component. Why? You can sort these among themselves, or you can rearrange all the numbers among themselves without paying any cost, right? You can just do some combination of swaps and put together things in the correct order. So let's say the connected component had an element j, had an element, or rather had an element I that was not at position I, but position I also belongs to this component. So you can move I to that position I without paying any cost, since you can do some combination of swaps between the same component, right? Does that make sense? So you can have multiple components, right? You can have this sort of a component, this is a component, and then so like this yellow is a component, and then you have these two. These are like their own components, kind of. So again, to reiterate, if an element I is not present at index I, but the index, say I is present at index j, so if I and j both belong to the same component, then you can move I from j to index I using some combination of swaps, and you won't pay any cost, since you can move it around using only the free swaps in its own component. Now, so let's make a new graph where all the like the nodes in the new graph are basically the components in our previous graph. So this is, say, a purple component. This is another purple component. We have a red component as well. And then we have a yellow component. Now there can obviously be some I here. Suppose we have the index I and index j. So index I is here, but the element I is present in a different component. That means you will add an edge from here to here. That means there is one element that wants to go from this component to this component, right? And it's actually these edges that you pay the cost for. So all these edges have a cost of 1, kind of. So we will not think of these as cost of 1, because it's not, so swapping has a cost of 1. Moving it around is not really a cost of 1. So point is, say we created this graph, something like this, and this will have some edge like this will have some edge like this, and this will again have some edge like this, right? And there can be multiple edges, correct? Between two components, there can be multiple. So what I want to do is, and this I haven't rigorously proved, is we can show that all the edges, all the directed edges, they can be decomposed into cycles. Okay, so a cycle is like this. There is something here that wants to go here, there is something here that wants to go here, there's something here that wants to go to this purple component, and then there's something in this purple component that wants to go to this I. And these are basically, so this is a cycle, and this is kind of the cycle that we talked about in the previous permutation problem, right? What's the difference between these two problems? The difference is that there, each node in the graph was a specific index, and each cycle, it was easier to think about the cycles because it was okay, this element is going to this position, then the element at that position is going to some other position, and so on. Here, inside these big components, kind of, these nodes kind of represent big components where you can have cycles, rather you can have swaps in between those components as well. So it's a bit harder to think, but yeah. So but effectively we are still doing the same thing. We are taking certain elements and we are taking everything along a cycle. Now there are a few key differences between this graph that we are talking about and the cycle graph in a permutation, in the generic cycle graph of a permutation. What are the differences? Firstly, there can be multiple edges because one component does not mean, like, one node does not represent a single node in our original graph. It represents a whole set of nodes, correct? Secondly, they are not disjoint. You can have intersecting cycles. Okay, so let's keep these 2 points in mind. Now, what is another observation that we can make? Similar to the previous problem, when we traverse one entire cycle, we can think about it as we are doing S, like if the cycle length is say S, we are doing S minus 1 swaps, correct? If we want to correct everything along the cycles, we are doing S minus 1 swaps. When I say swaps here, I mean inter-component swaps, not swaps in the actual permutation array. Because in the actual permutation array, you will also have multiple free swaps done. But I'm only talking about inter-component swaps, which actually you have to pay some cost for, right? So if you have a cycle of length S, you will do S minus 1 swaps. Now, what do I effectively have to minimize? The number of these swaps, right? So if I do X, if I can decompose all my edges and partition them into X distinct directed cycles, then what is the number of total swaps we need to do? Let the total number of edges be N, then we need to do N minus X swaps, right? So from here, we can kind of argue that, okay, if I can partition all my edges into the maximum number of directed circles, then this X quantity is maximized. Number of edges is anyway fixed, right? So we have to just maximize this X. So X will get maximized if we can partition all of our edges into the maximum number of directed cycles, right? So we have reduced our subproblem from trying to do swaps to trying to, like, we have formed a graph, a directed graph, where we want to partition all our edges into the maximum number of directed circles. So there can be multiple such decompositions, right? So in the editorial section, I was seeing someone's diagram that was kind of nice and makes my life easier. So yeah, so this diagram. So yeah. So this diagram, so this is one possible diagram that can happen, like rather the one possible combination of edges that you can get. So here you can have either 3 cyclic decompositions, like you can decompose them into 3 cycles, which are these green cycles, or you can decompose it into 2 cycles, which is this one yellow one, like using these 3 edges, and then this one outer cycle using the rest of the edges, right? So just as an example, so how do we actually do this? Well, the key observation is this N value can be really small. So N is something bounded by something like 18, right? Because see, every edge effectively represents a position, right? When I am saying that I have some edge from here to here, when I am saying that I have an edge from this yellow component to this red component, I effectively mean that some element wants to go from the yellow component to the red component. That some element is an element, rather is an index, right? So since we have an 18 length array, we cannot have more than 18 indexes, right? So the number, rather each index is each edge, rather each index is one edge at the worst case scenario if there are no free swaps. Anyway, so okay, forget about swaps here. So every edge is representative of a particular element. So there can be 18 edges, right? So whenever we see numbers that are so small, 18, so like how do you think about it? So we cannot generate all permutations. Permutation, it takes like 10 factorial is something like 3 is 7. So permutations, leave it aside. Can we generate all subsets? So these are the most brute force things that we can try to do. Can we generate all subsets? 2 to the power 18 is not so much, right? So 2 to the power 18 should be something like 5e5. Let me just see. So 2 square power is 2, 4, 8, 16, 16 into 4, right? Okay, 2e5. So not really much. So we can do a something. So the next idea that should come to our mind is doing something in bitmask DP. Okay. So see, we cannot really do something in a greedy way. DP is kind of what we always want to aim for. If our problem constraints are, at least for me, I try to kind of aim for some DP if there is no obvious greedy solution. If the constraints of the DP are kind of very high, then obviously we need to think of something else. But in this scenario, what is a possible bitmask DP that we can have? We can have something like, so we want to find the number, we want to partition the edges into maximum number of cycles, right? So first is used edges. So we will have a bitmask of used edges. Okay. We also need like few more states. So in this problem, it turns out that the states that you need are what is the initial vertex and what is the current vertex. So these are kind of the states that you need for the DP. This DP effectively represents, what does this DP mean? It means that you have a path from initial position, like vertex ini to vertex curl, and some more cycles. And what is the maximum number of cycles you have been able to decompose it into, right? So yeah, so you have like ini to curl straight path, and what is the maximum number of cycles you have been able to decompose the rest of the edges into. So instead of writing the transitions out myself again, I'll refer to the setters code as it's pretty neat. So just this portion. So there is nothing fancy about using a char data type here. So just so you know, like you can just use int as well, I guess. So yeah. So this is a top-down approach, right? So this is a top-down approach, not a bottom-up approach. So what we effectively do here is we have some mask, right? Mask is effectively what all subset of edges that we are currently using. So now what do we do? If initial is equal to current and mask is 0, mask 0 means we are not using any edge, right? So then we will just return 1, right? There's one possible path only. So this is a base case. Now what if initial is equal to current? So we are kind of not dealing with any straight paths right now. Everything is in the form of a cycle. Well, the DP state, like the transition should be pretty clear, right? We are just iterating over all the edges that we can have, and then trying to see that, okay, what is the last edge that I traversed? Okay, so that's what I'm kind of trying to do. What is the last edge that I traversed? And effectively we are subtracting from the mask, rather we are removing from the mask that last edge, right? And this is like the usual bitmask DP transition. For the path case also, so bitmask DP, how do we think about it? We usually think about it is, okay, so we have this mask, so this is what we have done. We have some other states. What is the last possible thing that we have added in my mask? So I want to find that, okay, if I had removed, if I don't include this last thing, what is the number of ways, or what is the answer for the rest of the thing? And then after that, if I add this edge, then it's my current state. So I derive my answer like that. After that, it's kind of a pretty standard bitmask DP. So yeah, so this is like the full solution for the problem. So just to reiterate on what I was saying about this bitmask DP, if it kind of helps. So if you have any sort of bitmask DP, so if you have any sort of bitmask DP, what you want to do is you have some DP mask and you have some additional, let's say, some other uh, vertex. Okay. Now, what you want to do in transition is fix the last element that you added to your mask. Okay, like fix some last element, and then you basically derive your answer from DP mask minus last element, right? And prev vertex. So I'm saying vertex here, but you can like it, the second state depends on what the problem is, right? So you kind of want to derive your answer from a shorter bit mask. So when you remove some item from the bit mask, obviously the number of ones lessens, right? So yeah, so the mask does not denote the robot swaps. The mask denotes the number of edges that we have used. So the number of edges, what I mean by that, rather the subset of edges in my last graph. Remember our last graph where the edges, the directed edges were only the swaps that chef uses, or rather it was not even the swaps, it was actually a number, rather an index. So wait, I cannot go back. There's the history option. Okay, there does not seem to be a history option. So remember how we had drawn components here? So this was one component, this was one component. We drew an edge from this component to this when there was a certain element I that was actually present in this component, but its original position or its position in the identity permutation would have been in this component. We cannot go from one component to another using robot swaps. We must have used certain other chef swaps, right? So our claim was that there will be certain cycles. We can solve, we can like decompose the cycles into swaps. If a cycle had length s, we had s minus 1 swaps. We want to maximize the number of directed cycles. So we are trying to just denote what are like maximize the number of directed cycles using bitmask DP. The mask denotes the subset of edges, these edges, right? These edges that our graph has. So the problem that we are trying to solve here is a bit like a different subproblem. Like it's a subproblem that essentially solves our previous problem, but it is not directly related. So yeah, hope this clears it up. This was a bit of a hard problem, not as easy as the first 2 or 3 problems, but yeah. So the rest of the problems, we will probably discuss it on Thursday or Friday, or I'm not sure, like we will let you know. So any other questions? Dry running on an example, we cannot just do the last part. It's like the bitmask DP part is very hard to kind of dry run. I mean, you have to uh, like it will be a big example, and like so yeah. I can still try maybe. So I can just give you a brief idea. So the brief idea is like, say your mask is something like you have 5 edges, let's say, right? So you have the edges are 1 to 2, 2 to 3, 3 to 4, 4 to 5, something like this. And then your mask represents is, let's say, 0 1 1 0 1, right? Something like this. This represents, you have you have 4 edges. Let's say you have 5 edges. 5 to 1 is also an edge. So this represents, this edge is not there, not, this edge is there. Let me represent this as just no. This edge is contained in my mask. This edge is contained in my mask. This edge is contained in my mask. This edge is, sorry, this edge is not contained, and the last edge is also contained in my mask, right? And let's say this was our mask, and initial and current were, so let's say ini and cur was respectively, let's say current is, okay, let me give a better example actually. So we have 1 to 2, 2 to 3, let's keep this at 2 to 4 as well. So this might not be actually a correct thing, but I'm just showing how we do the transitions. So let's say current initial was 1, doesn't really matter. Current was, let's say, 4. So what are the, and let's say we had this mask. So what are the last edges that we might have used? We could have used the edge 2, we could have used the edge 3, right? To get to 4, we need to have used the edge 2 or the edge 3. So let's say I use the edge 2 first. Okay, so what is the case, what is the DP state that we derive our answer from? So we have ini as 1, this is 2, right? And the mask is, so the mask is 0. We had not used that edge as of yet. So we have not used edge 2 as of yet in that DP state. After that DP state, we use edge 2 and we get this mask, right? So we get our, so this actually contributes back here. And similarly, another case that also contributes, I guess, is 1 3 0 1 0. Let me indent them so that, yeah, so something like this. So this is not exactly a correct dry run of the problem example, but I'm kind of trying to give you the intuition as how to do bitmask DP in general. So you take the last possible thing that you could have done. That is usually a thing that was present in the mask. You remove it from the mask. You go back, like, what is the previous state that you got derived your answer from. The mask will not have that specific element, and one of your other states will also change according to what last thing that you used. Hopefully that makes sense. Like, this is how you kind of approach bitmask DP. Yeah. So like, if there are some certain things that you still are a bit like hazy in your mind, I would definitely recommend you to read all the editorials. They are really well written, so hopefully they will clear all the rest of your doubts. Think about these as well if you don't directly get it, and then read the editorials. I guess that's it for today.